Okay, so starting a playlist for this book here, Generalized Linear Models with Examples in R. I would recommend this book. It's pretty accessible, especially if you're not, if you have a little bit of experience with linear models. And yeah. So anyway, I would check out this book if you can, or if you're interested. But here we go. So we're in chapter 1, and we have question 1.1. So the plots in figure 1.7, which I've copied and pasted right here, show the strength of Kraft paper for different percentages of hardwood concentration. And none of that is really important, but we have different models. So we have a quadratic model, we have a cubic model, and a quartic model. So in other words, the quadratic model has an x and an x squared, and the cubic model has an x and an x squared and an x cubed, and the quartic model has an x and an x squared and an x cubed and an x to the 4th power as explanatory variables. Okay? And so we want to figure out, we're not really figuring out anything, but we're just trying to get a sense for which systematic component, which is either x plus x squared or x plus x squared and x cubed, and so on and so forth, seems most suitable for our data. Okay, so recall that our linear models have a systematic component as well as a random component. Okay, and so it might look something like this. So we have a data point y, and then we have the systematic component, which is often denoted with this eta term, and an error term, or the random component, which is denoted epsilon. Okay. Now this eta component in the linear models that we will be concerned with in this book typically take on a form of x beta, where x is an observed data point and then beta is a parameter that we estimate. And it basically says how important is this predictor variable x in determining y. Okay. So notice then that so let's just kind of relate this here. So each one of these data points, okay, in these figures is a y value, okay, and we're saying that each one of these y values has a systematic component, okay, which is being represented by the solid line, as well as an error or a random component, which is the deviation, or I shouldn't say deviation because that has a technical term, but we'll just say the difference between the solid line and the actual observed value. Okay, so again we have the systematic component represented by the solid line, and then the random component, which is represented by the value of y that is not accounted for by the solid line. All right. So another way that we could say this is that the estimated value for y, which is denoted y hat, is the systematic component, is eta, is x beta. Okay. So here we're just really asked to eyeball these things. Okay. And so to my eye, it certainly looks like the cubic model and the quartic model are fitting the data best. Okay. And so it's probably one of these, right? They seem to be doing better than the quadratic model, right? The errors, the distance between the systematic component and the actual observed value seems to be greater generally with the quadratic model than the other two models. Okay, so one of these two models is probably best, and let's just say that the cubic and the quartic are equally good in terms of the distance between the data points and the systematic component. Well, in this case, we would tend to prefer the cubic model because it is simpler. It has fewer terms. Remember, the cubic model has an x, x squared, x cubed, whereas the quartic has x, x squared, x cubed, and an additional x to the 4th power, right? And so we will also tend to try to look for simpler models, if all else being equal, in terms of how well they are fitting the data. Okay, that is it for this very simple one at the beginning of the answers for this book.